Hello and welcome to Calculus Tutorial. We are looking at integrals still and antiderivatives. And this time we're going to take a look at the difference between an indefinite integral, which is what we've been doing mostly, and the definite integral, which we haven't looked at yet. Up until now I haven't really given you a good reason why it's called an indefinite integral. So now we're going to compare the indefinite with the definite, and hopefully those words, those qualifiers, will make a little bit more sense to you. And the best way I think I can introduce that is with a very, very simple word problem. So you can see the difference between a definite and an indefinite integral. So imagine you are walking down the sidewalk at 5 miles an hour. And we're going to take a look at our position, our velocity, and while there is an acceleration graph, because you're walking at a constant 5 miles an hour, there won't be any acceleration, so we're not going to worry about that. We're just going to worry about velocity and position. So if we're walking along at 5 miles per hour, our velocity graph is nice and boring. It will be a horizontal line right here at 5. And you can go 1 hour, 2 hours, nice long walk, 3 hours. And so if we want to go backwards to position, we would simply take the integral of 5 dt. And that would give us 5t plus c. Because you might start somewhere besides 0. And let's do that. Let's say we start 10 miles away. Alright, so there's 5, 10. And then we have to do this equation. So if we start 10 miles away, that means c is actually equal to 10. So there is our position function, 5t plus 10. That is our indefinite integral. Okay? It tells you where you are. It's your position. And so if we draw that graph now, we're going to go over 1, up 5, over 1, up 5, over 1, up 5, etc. And we'll have a nice linear line like that. 15, 20, 25, etc. That is our indefinite integral. The definite integral sort of connects these two ideas. And so the definite integral looks like this. Let's say we think about the integral from 0 to 3 of 5 dt. And so what that does is it looks at our graph over here, and then it takes the area underneath the curve. Take a look at this area here. Because we're taking the antiderivative, or the definite integral of 5, which is this function over here. What is that area? Well, our height is 5, our length is 3, so that is 15. Hopefully you can sort of see the 15 in there. Does that have anything to do with this over here? Yes, there's a 15 here, but that doesn't seem to have much to do with what we're doing here. Let me put in the time. 1, 2, 3. You don't see the number 15 until you take a look at how far we went in those 3 hours. So we started here at 10. 3 hours later, we're now up here at 25. What is 25 minus 10? 15. Kind of weird that the area underneath the curve here is equal to how much we rose the rise over here. That is our definite integral. It's the area underneath the curve. So the area underneath the curve, the area under 5, is equal to how much we rose on our position function, which is this one. And that is how far you traveled. From hour 0 to hour 3, we traveled 15 miles. Is that where we are? No, we're up here at 25 miles away. But we traveled an extra 15 miles. So this one sort of tells you how far you went. And so the difficult thing here is for a definite integral, it tells you how far. But for an indefinite integral, it tells you where you are. And we're going to have to sort of keep those things straight in our mind. How far you went is not where you are. Are they related? Yes, but they are not the same. So your indefinite is your actual position function, and your definite is how far you went. All right, so in a nutshell, if you're going to do a definite integral, it's the area underneath the curve, this 15 right here. So we're going to practice that a little bit to see how that works just by working on the math. So definite integral. So if I want the definite integral from 1 to 4 of 3x minus 1, that will be the area under this curve from 1 to 4. So if I think about that graph, I'm going to draw a quick sketch here. 3x minus 1 starts down here at negative 1, goes over 1, up 3, 1, 2, 3, over 1, up 3, 1, 2, 3, etc., like that, until eventually we come to the point here at 4. 4 comma what? If I plug in 4, 12 minus 1 is 11. And if I start at 1, that is the point. Let's see, if we plug in 1, 3 minus 1 is 2. So 1 comma 2. I want the area under the curve from 1 all the way to 4. So draw that shape. Draw that down. Draw that down. We want this area in here. Now, to do that, it's probably easiest to break that into a couple of shapes. Draw this straight over that way. Now I have a rectangle and a triangle, both easy to find the area of. So the base here is 3, the height is 2. So 3 times 2, that area is 6. Now the triangle, the base is again 3, but the height, the total height is 11, but 2 of it is right here, so this height is actually 9. 9 times 3 is 27. 27 divided by 2 is 13.5. So the total area, you're going to have to add those up. 13.5 plus 6 is equal to 19.5. So that definite integral is equal to 19.5. And so again, we're just finding the area under the curve. So all this space in here is what we're finding. All right, let's do one more. So there we had an equation. We had to make the graph ourselves. Sometimes you are given the graph to begin with. So here we have a piecewise function made up of linear equations and a half circle. So first I want the definite integral from -4. So from here, from here, all the way to -1 here. So that gives us this area right there. Looks like we're going to want to break this up into a few shapes, doesn't it? Kind of a complicated area. So one of them, I'm going to make a rectangle from here down, I think, is going to be the easiest. There we go. Kind of like that. So I've got a nice triangle over here that will be easy to find the area, a nice rectangle, another nice triangle. So this rectangle is 2 times 1. That area is 2. This triangle, the base is 2. The height is also 2. 2 times 2 is 4. Divided by 2 is 2. Kind of nice. And then this triangle will be 1 times 3 divided by 2, 1.5. So total we have 4. 5.5 is that area. All right, now we want to find the area from -4 here all the way to 3. All right, well, that's going to be kind of nice because we already know the area from -4 to 1. It's 5.5. Now we just have to tack on this half circle and this triangle here. Let's talk about the triangle first. I think that will be a little easier to talk about what happens when your graph goes underneath the x-axis. So this base here is still 2, but because the graph is going down underneath the x-axis, you can think of this dimension as -1. 2 times -1 is -2 divided by 2. This area is -1. And so the rule there is anything below the x-axis is going to be negative. Anything above the x-axis will be positive. So the half circle here will also be negative. And we just have to find that area formula. A circle is pi r squared for the full thing. And so for only half of it, it will be pi r squared divided by 2. The radius is 1, so that will just be the full circle. Pi r squared would just be pi. Half a circle will be pi over 2. So because it's only half a circle, that will be pi over 2, and because it's underneath the curve, underneath the x-axis, it is negative. So we combine all these, minus pi over 2, minus 1. And just to keep our numbers nice, I won't make that decimal. So 5.5 minus the 1 is 4.5 minus pi over 2. If you really want a decimal, you can subtract those on your calculator. But the concept is there. So a definite integral is the area underneath the curve, or between the graph and the x-axis. If it's below the x-axis, your area is technically negative. All right, so hopefully that makes some sense to you for definite integrals. We have 2 types of integrals or antiderivatives that we can do, the definite and the indefinite. Another way to think of that is the definite are numbers, whereas the indefinite are equations. And that has a parallel in derivatives. There were 2 ways to do the derivative. You can take the derivative and get an equation, or you can actually find the slope at one point and it will give you a number. So we have those two different types in both derivatives and antiderivatives, where you can get an equation or a number.